Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, students. Peace and blessings for you all. Today we're gonna start our lecture series on the computer compiler design. Okay. The first thing we deal here is compiler versus interpreter, which we already know. There's no problem in that. So, in case of a compiler or firstly the interpreter. Which is constituted as online. Why? Because we have program and data, and you give it to the interpreter, and it directly converts into the output. And while in case of a compiler, you have a source code, and that source code is converted to another program, which is executable code or some kind of object code, which may be the assembly code. Okay, which is which we call as a target program sometimes, which will run on a target machine later on, taking the data and gives the output. That's why we call it the offline. For interpretation, you need to have an environment which understands the language. For example, we have an array and index I, we put up something like 20 into it. Now our environment, which is a kind of a virtual machine in case of the interpreter, which understands the dimensions of an array and puts directly 20 into it. But in case of compilation, we don't. We first create some target program, and later on we take data and put stuff into that. So this seems to be a little slower and not efficient, but in fact compiler is efficient than the interpreter. But interpreter is sometimes used like debugging, where we do direct compilation of line by line to check the errors and all these things. And there are many languages which prefer interpretation because of certain reasons we talk about later. But the compiler is actually the faster one. It is more efficient because here we can do some kind of tweaking. We can make it more faster. We can make it what's called an optimization technically. We can do a lot of optimizations here, which is not possible here. Okay, and we have compiled a program once, and you can run that many times. But here, all the time you try to execute a line of code, you have to interpret it all the time. So that's why it becomes slower and more slower, and it becomes faster because you have already done it. So, for example, there's a loop, and you are interpreting it all the time. But here you have done it once. You don't need to convert that again and again. And to run a program from this target program is much easier and faster than what to do in the interpretation. Let's before we dive into the compiler, we talk a little bit about the compiler history. Actually, in 1953, IBM develops the 701, what's called EDPM, Electronic Data Processing Machine. That was the first general-purpose computer built as a defense calculator in the Korean War. After this, in 1954, we actually have some kind of compiler, but we had no high-level languages at that time. So we were doing programming was done in machine and assembly language. Okay, so that was the key because that inculcated the cost. It was not on the hardware cost, but the software cost as well. So we had early computers, hardware was costly, but now the software cost had increased because there was the complexity of the assembly program and all those things. Then basically the software cost actually increased, surpassed the hardware cost. So that was the key to trigger something called compiler. So idea started in 1953. John Backus, he came up with the idea of speed coding, to develop an environment and just do something quickly. and he developed the first interpreter. But it was, the drawback was it was 10 to 20 times slower than programs written in assembly. Okay, so there's something to do better than this. About that interpreter, I would like to add one more sentence to it. Basically, it was 10 to 20x slower, but it also took 30% of memory. In those days, memory was not today we have GBs and all those. We had terabytes of memories, but in those days, it took 300 bytes of memory. That means 30% of the total memory in those days. So that was a huge ask. So that's why the John Backus in 1954, took up the second project called Fortran 1. Okay, 1954 to 1957, I guess it was, the Fortran 1. Actually, Backus and his team released a research paper titled Preliminary Report Specification for the IBM Mathematical Formula Translating System Fortran. In fact, the initial release of Fortran was in 1956, and which is a 25,000 lines of assembly code. And so we got the Fortran 1 actually. Okay, what's called a formula translated. And we had around 50% of programming was done in the Fortran, so it was really successful project. It was faster because projects that took 2 weeks to write, now it will take only 2 hours, which was earlier than assembly. So in 1958, we have 50%, as I said, programs written in the Fortran. Okay. Actually, this was the first compiler, we can say. Okay. It had a huge impact on the computer science as well, and it led to the enormous body of theoretical work as well. Okay, and the today's modern compilers actually they have the same outline of Fortran 1. Today we may have a lot of things, but the basic framework is the same what we have in the Fortran 1, which is given by the John Backus. Okay. So let's recap a bit of what we have learned until now. So we have a program language. We can implement it in two major strategies. One is the interpreter, which is old and it's much less studied, and then compiler, very well understood in mathematical foundations. Some environments provide both, for interpreter and compiler, like Lisp, Scheme, etc. We have here the interpreter for development and compiler for deployment. And Java, in case of Java, we have a Java compiler which creates the bytecode, which is interpretable. Then we got a just-in-time compiler, which converts the bytecode to the executable image, right? Okay. We know 704 in 1954. Where all programming is done as assembly. So cost of software exceeds cost of hardware. So we have a low productivity. So John Backus came up with the speed coding. So he created an interpreter, but which was 10 to 20 times slower. So he started the second idea in 1954. He proposed a program that translated high-level expressions into the native machine code. There was skepticism, but it revolutionized it because the whole scenario. And we got a Fortran 1 project. That was the first compiler was released. Now that first compiler had a huge impact on the programming language and computer science. And a whole new field of compiler design was started. Okay, and 50% of programming, it was very successful. Fortran, around 1958, 50% programs in Fortran, and the development time was cut down to half. As I said, 2 weeks, which you wrote in assembly, you write in 2 hours time. So it's really a lot of gain. So led to the enormous amount of theoretical work which I was talking about, like lexical analysis, parsing, optimization, structured programming, code generation, error recovery, etc. And I said that modern compilers preserve the basic structure of Fortran 1 compiler. Now, having understood all these things, now you guys should understand and dive into the black box called compiler. And just until now, we just saw, all the time in the previous programming language as well, we talk compilers as one box, but now it's time to dive into that box and see what parts it has inside. Now, a compiler must perform, two major tasks. One is the analysis. So basically, compiler has two parts: one is the analysis part, one is the synthesis part. Analysis does the analysis of source program, and synthesis does what? It synthesizes actually machine language program. So it deals with the hardware, so machine dependent part, and this one is the machine actually independent part. Okay. So let's talk. This is sometimes also called the front end versus the back end, and in between we have some kind of code optimization, which is actually optional. And we may have also the people optimization, which is done in this part, and which we discuss later on. Now, if we open up the box of the compiler, we'll see many parts. Okay. So first thing what we do is we have is the lexical analyzer. It's also called sometimes the scanner. Then we have a syntax analyzer, semantic analyzer, and then we have intermediate code generator. And up to this, what we're talking about is the front end, okay, or analysis part. And after that, when we start generating some kind of code, it is machine dependent part. So, or a synthesis part, or the backend part. Okay, we got an intermediate code generator, we got machine independent code optimizer, and we got basically the backend is from here. Okay, this is the optional optimization part. This is the code generator and the machine dependent code optimizer. Where we see the default optimization and all those things. And we also have the symbol table, which we'll see just in a while, what it does. Okay, so we have to understand one by one these layers and these parts, these subparts of the compiler, to understand exactly the compiler construction and compiler design. Okay, so let's talk about the first thing, what's called as a lexical analyzer or a scanner. So which takes a source program, which is untapped character stream, and what it output of the lexical analyzer or scanner is a token string. Okay, so let's concentrate now on the lexical analyzer. So let's deal with the lexical analysis, or also called the scanner, because we're trying to understand the language. Okay, so what is the first thing we will do to understand language is to understand the words, to see which words are actually the correct words and which are not correct words. If, for example, I write it like this, now if you look at it, this is a kind of no, I have misplaced the white spaces. This is I am teaching compiler, okay, but I'm misplaced the the white spaces. So we need some sort of rules to understand why we have the word breaks, to get the words out of it. So if I'm saying I am, then there is space and TE, because if we have a rule that the white space breaks the words, then it's not a correct word. Okay, so I have to, after I have white space, then am, then white space, then I'm saying teaching, and so on. So this white space actually is a kind of rule, is actually a rule which breaks these words into some words, and these words should be having some meanings. Okay, the proper words. They should be these words. For example, if I'm saying I am, if I say I am a, Now, MA is not a word in English, so we can generate an error while reading to say that, hey, this is not a right word. So this is what lexical analysis does. Its job is to identify the correct words, also called the lexemes. Okay, so what is a lexeme? So your lexical analyzer just reads the characters, because whatever it has, it doesn't know whatever is coming, it takes it as a characters. So it has some rules as per the language to identify those words put into the language. Okay. So lexical analyzer actually checks the source program, and it groups these characters into some meaningful sequences, or what we call the lexemes. Okay, so this is what's called as a lexemes. So for when it identifies a lexeme, okay, it identifies a lexeme from these characters. Okay, whatever the characters coming, it identifies the lexemes from these characters, and it generates what's called as a token, or you may call it a word, if you like, in English. Okay. Uh, it is the token is it is the output of that lexeme. Okay, and the token which it generates for that lexeme. So what's a lexeme? It's a group of characters which has some sense, we can say. Okay, meaningful sequence of characters. Okay, for example, if I say a code, if A equals to B, then do this, whatever. When I see IF, it understood it's a meaningful word, so it creates a lexeme for it. It's a lexeme for it. Okay, for lexical analyzer, it's a lexeme. Okay, and for this lexeme, it creates a token, and a token has two kind of things in it. Okay, now a token has two kind of things. Now, if I say token, token has two things in it. One is the token name, and we've got another one is the attribute name. Okay, so what is this token name and attribute name? Before understanding it, let me give an example. For example, we got like here is equal like this: A equals to B, okay, plus C into some constant, say 20, for example. Okay. Now these variables which we don't know, maybe before the statement we may have the int A comma B comma C. We may have defined ABC as a type integer. So when I defined it, so compiler would have created a symbol table for this. Okay, where we have some kind of serial number, then we have some kind of whatever the variable is, and whatever the type is. Okay, what is the type of that variable? Say for example serial number 1, at the serial number 1 we have said this is A and this is of type int. At serial number 2 we got, say for example, C and it's also type int. At serial number 3 we got something like, say, 20 or something like that. Okay. Actually for 20 this is a constant, so we don't need an identifier for this, right? So I left it out. And there was a and then maybe this is a B and this is a C. Okay. For 20 we don't need because this is a constant, so it doesn't have an identifier. So if we try to create a token for this A, for example, we understood that this is a lexeme. Okay, A is a lexeme, and we have a proper entry in the symbol table. This is my symbol table as well for this A, and so I may create a token for this, which is saying ID, identifier, and comma, and what is the location in the symbol table? That is the 1. So we have the token name. Do you understand? Yes? Okay. So we have a token name. Okay, and the token name is actually an abstract, you know, name, right? It's an abstract symbol, um, which is standing for the identifier. For example, here, ID, uh, and this the second one is the attribute name that points to the symbol table. So you can understand this is which points to symbol table. Okay, and this is this one we may be interested in the second part, was a syntax analysis. Getting me? So if we wanna convert this whole thing now, that is uh, for equals to, if we say equals to, we may say, for example, token name assign, and maybe we have the equals. Okay, or alternatively we can simply say equals, no need to say assign, because compiler know already these things. Okay, the operators uh, as well, like plus, into, and also this assign equal to sum. So we may say assign or something, or we may omit the token name. We'll directly say equals. In fact, if I have to write this, I'm writing it in the wrong way. I should not have written it like this. I should have written it equals to, because this is the token name, and then assign. Okay, but we may omit actually this attribute name as well, because it doesn't have anything in a symbol table, because we already know it. So you can write it simply as an equal. So we may continue in the same way, and then for we have, let's have a look at the pen. Where is the pen? Here. Okay. Say for example, now we have what is called as this B. We can use, this is my ID, and I will use it to see attribute name 2, which is actually the symbol table entry. Similarly, we got a plus. We can simply say plus. We got C, and we got, again, this is an ID, and then we say it is at the position 3 in a symbol table. Then we got a star, and this will be simply star, and then we got a 20. At 20 we can have a, we can say 20 like this, but actually we should not do like this. We should actually rather do the like this. For example, number, and then 20, or say 4, for example, 4, because the 4 is a symbol table entry where we have an interrepresentation of 20, because we may have the different representations for many constants. If for example, the floating point constant, so that have a totally different representation than the integer constant. Okay, 20. So we may simply say number, and then we say 4, which actually tells us where exactly. So 4 points to the symbol table for interrepresentation, yeah, of this 20, and so on. So this is our output, what we call the tokens from our lexical analyzer. So we just said that our this is our lexical analyzer, or scanner. It scans the character stream of the source code, which it takes it as a characters and identifies the lexemes and creates equivalent tokens for that for those lexemes, and then these tokens are given to the next guy, which is the syntax analyzer, right? One more thing, the symbol table which I have put up here is not as simple as this. This is just for example purposes, okay? It will have a detailed and complex structure. So if you say, for example, if x is equals 20, then you're going to do something like say we have if x is put in b something, put in b some 24, else you can do put in b, say for example 30. Now this will be all like character stream, so we have to understand from it some lexemes. So what would happen is when the scanner or the lexemes scans the characters, it generates the if. So if we see the simple DFA of it, so we say like this, for example, we start and we say I is coming, then F is coming, okay, and after that there is a white space. So our white space is a rule to identify that we have a break. So what we are using, and we'll talk about that later on, here's my pen. Okay, what we're using here is a finite state automata, okay, rather than push down automata, which we'll see in the next phase, PDA, in the parsing. So finite state automata is which we'll be using in the lexical analysis or scanner. So we need to have some, DFAs where we understand our matches for the regular expressions and all. Okay, because we model using regular expressions, and we recognize our lexemes using finite state automata. Okay, maybe we use a DFA or something else. We'll talk about in detail later on, and we talk about the next phase where we talk about PDA, push down automata, where we have a sort of grammar and context-free grammars and all those things. So in general, we're talking about that in the lexical analysis. This is the overview video. So in detail we'll see later on that the lexemes are identified using the FSA, and a token is generated to that lexeme, and which is now fed to the next phase, which is called as a parsing. Okay. So in a syntax analysis or parsing, if we have an analogy of the English, so we said the first thing was to identify the words. What is the second thing? Second thing is gonna be to identify the grammar, right? 1 second. Use the pen. The second thing will be to understand the grammar. Is going on. So we have understood the words. Now we have to understand the grammar. Is it? So for example, I say some sentence. So what we are trying to do is we are trying to understand the first we understood the words. Now we try to understand the structure of a sentence. Okay, and that gives some. We can have some diagram representation like a tree. So let's take some sentence. Say for example, this boy is a good. Maybe some cricketer or something. Okay, cricketer. Why is it not writing? Now, what is this boy? What is this in this sentence? This is gonna be the article. Okay, the boy is noun. Now, this is the word. Okay, and again an article. This may be the adjective, and this is gonna be the noun. Now, if you look at this part here, this is my subject, and this is going to be the object. And if you combine together, this is a sentence. This is an object. And if we say this is actually a sentence. Now if you see, this is my root, and they have two branches, and then they have the sub branch and so on, the leaves. So if we take an example, another example of programming language now, I'm not able to find this pointer. Okay. Say for example we say some sentence. If x equals to 2, for example, then we say then put in some another variable b equals to say 1, else maybe in the b equals to 0. Okay. Now, firstly, we may have the lexical analysis, which will generate the tokens for all of these guys and try to see the lexems in this program structure. Then we will say that we have an if then else block. Okay, we have an if then else. Okay, now we may have a predicate, which is here. Okay, and that produces actually a relation which is saying x is equal to y. That's a relation, that's predicate that belongs to the if and else. Then we may have the then block, and we may have the if block, else block. Okay. Now in the then we have again the assign, we have the assignment. In the else also we have the assignment. And in this we have what we have act b. Okay, we have in this we have. Let me get it up. Sorry, let me just write it down. Okay, in this we have got b equal to something about that equals 1. In this we got b equals to 0 or something like that. I don't remember what I wrote. Yeah. Now this then belongs to anything else, also belongs to anything else. Now we have the structure like this. Okay. Now this kind of tree structure is called the parse tree. Okay, it's trying to give a structure of the sentence. So how it actually flows, how the structure is, how this sentence, how this piece of code is actually organized. Is it? Now if you take up the example which we had taken up earlier, a equals to b plus c into 20, the Lexical Analyzer will generate the tokens as these, and then we have the syntax analyzer which will generate a parse tree which tells us the structure of the sentence. In this case, equals to will be happen only when we have a plus. Plus will happen only if we have a star. So this ordering is very important because it tells us the precedence of the operators as well here. Because firstly the star will apply the multiplication, then whatever the output is to the addition, and that will assign to the ID1. So this is the consistent way of doing things. Now this syntax tree, or what is called the parse tree, is fed to the semantic analysis, which actually chucks a sense of the things, and it will go on, it will give it to the further parts. Okay, so now that means we have to read now the third thing, that's called the semantic analysis. Now in the semantic analysis, we're trying to understand the meaning of a sentence. For example, we say Junaid said Junaid is at home. So is this Junaid two different people? Okay, how many people are there? Is it two? Is it one? Or it may be three. Okay, if I say something like this, say for example, A equals to B plus C. Now syntactically it's wrong. There's no problem with the syntax. Okay, our syntax analyzer or parser will generate a tree, and it has no problem with this. But semantically this may be wrong. For example, say for example, A is of type character, and B is of type float, and C is of type int. So what I'm trying to do, you're trying to add two floating point integer numbers. Now you are trying to assign that to the character. So now if you see the semantics of this statement, it's going to generate error, right? Syntax wise, it is no problem. You're trying to assign, and there is some plus, there is an A, there is a B variables. No problem with that in up to step 2. But step 3 now kicks in and generates an error because the semantics is wrong. Because you are trying to assign character variable something which it can't take, right? So these things have to take care of in the semantic analysis. Now the syntax analyzer uses the syntax tree as well as the symbol table to see the consistencies of the semantics of the program according to the programming language, or or the language definition, we can say, right? Now it may gather information, and it may save it into the syntax tree or a symbol table as well, which will be used for further in the code generation, intermediate code generation as well. So one of the important thing was the type checking. We just saw that it's called a type checking. Okay, so you have to check the type. Whether, for example, we have an array here of say, for example, now I'm saying I, and I is of type float. Okay, I assigned somewhere the value of I to be like, let's say, for example, 2.0 or something like that. Now you're trying to assign, you're writing here a of I, but we know that array of index has to be integer, so it is again the type checking problem. So this will be caught with semantic, because now syntax wise it's not a problem, right? It's okay, but semantic wise it's wrong, so we have to stop here. It also does what's called as the type coercion. For example, in type coercion what we have is automatic conversion from one data type to another data type. For example, we have say we say, for example, our example is equal to b plus c into 20. For example, the c may be a floating point. This c is floating point, okay, and this 20 is constant, integer constant. So what it will try to coerce, okay. So this may be this 20 before applied to the multiplication, this may be coerced, means this may be uplifted or upgraded to the floating point. Maybe we say into float 20. So this will convert this 20 to the floating point, and then there is no problem with the multiplication. So this type coercion is done by the semantic analyzer as well, because it understands the semantics and so it applies accordingly. It also disambiguates. We will take them in detail later on. So for example, we got a plus b. Maybe these are this time characters. So plus is a concatenation operator. So if a and b are the floating point numbers, then there is a floating point addition. Okay, they may be integers, and then this plus has to do addition to the floating point number. So these things are also understood and done by the semantic analyzer. We'll take up semantic analyzer later on. Okay, I'm going to see all those things. So now we will add a little bit here. So Lexical Analyzer, which connect tokens, and then we have the parse tree here. Now this parse tree, in a semantic analysis, we do only one thing, that is the type portion here. This node is added, okay, into float. We have a lot of things in it. Just for simplicity, we have set into float to make it done to type portion here, right? So we may have a lot of things which semantic analysis does, which we take up as a separate chapter in the semantic analysis. Now after semantic analysis, we may have what's called intermediate code generation. Okay. Now while translating from the source code to the target code, a compiler may construct more intermediate representations. The parse tree was also the intermediate representation, but we somewhat like machine language. We need some kind of intermediate representation, which is not actually specific to a particular machine, but more kind of a general thing. For example, we have one of the things is called 3 address code. Okay, so our this 3 address code is for an abstract machine. Okay, it's not for some specific machine or something like that, right? It's for an abstract machine. We have to understand that thing.